In this segment, we'll look at the generalized uncertainty principle because we have enough machinery with the Dirac notation to relatively easily get a very generalized form for the uncertainty principle that's good for any two quantum mechanical operators, really. And it really there are other generalized uncertainty principles, but this one is been found to be the most useful. But I've seen a number of other generalized uncertainty principles that are I guess maybe useful in very specific circumstances. But most of the time, this one that is presented here will be the one that you will wind up going to. Yeah. And here I want to sort of set the stage because we'll be looking at two physical quantities that we know in quantum mechanics are always represented by their corresponding Hermitian operators. So these operators A and B are Hermitian, and we associate those to things that are physical and measurable that produce then real numbers in any measurement. Uh, we know that any system is described by a ket vector, and I'll represent it here by the ket of psi. And I'm also going to assume that we have a normalized ket so that the psi inner product with itself is just 1. And then just to recall a little bit of our notation on this, uh, the the average value of many measurements is the expectation value. So many measurements of the physical quantity A. In quantum mechanics, we sometimes represent it like this, or it's the expectation value of the operator. And by this expression, we mean that we take the operator and bracket it in between the state of the system, the bra and the ket of it. By the time you evaluate this, you're down to a pure single number, and it's a real number. And I think of this as being that real number that represents the average value of many measurements of similar systems. Similarly, for B, its expectation value is the bracket of B operator for the same system. And then with those, you can use these numbers here and define the standard deviation of A squared. And remember, the standard deviation is the deviation of a quantity from the mean, from its average value, squared. And so, but really just by definition, it's the expectation value of this operator here. And again, this is just sandwiched in between psi and psi star, or psi, ket psi, and bra psi. And likewise here, B, the standard deviation in B squared is really just by definition the expectation value of the deviation of B from its average values, all quantities, average value quantity squared. And again, these brackets are meant to be a shorthand notation for I bracket this in between the state of the system. So this operator bracketed here to evaluate down to a number. Those are real numbers. This quantity here are both real numbers. Pretty easy to see because A is Hermitian, and I'm just subtracting a number. So this operator A minus the expectation value is Hermitian, and so it's any measurements have to be real numbers, and likewise the average value of those measurements has to be a real number. In fact, since it's squared, it has to be a positive, definite real number. In any event, with this notation, we can make a statement of the generalized uncertainty principle. This is the form I think that your book uses, which is really not my favorite form, but I'll use this just so that we match up with the book's notation a little bit. And that is that if I take the standard deviation of A squared times the standard deviation of B squared, that product of those two has to be greater than or equal to this quantity in brackets here. And this is the expectation value the commutator of A and B, where A and B are the quantum mechanical operators associated with physical quantity A and physical quantity B, respectively. Now, it turns out in cases of usual interest, this quantity inside is a real number, and so when you square it, you get a positive real number. And so I can, all these things are squares, and so I can take the square root of both sides, and you still have standard deviation of A times the standard deviation of B is the absolute value of this quantity. Sometimes they use this off, they leave this off, but I guess this way there's no question about the fact that you want the positive root here. There's really two roots, a positive and a negative to this, but we want the positive one. In some sense, the demonstration of the generalized uncertainty principle hinges on a kind of a trivial observation, really. And that's here for a complex number z. Z is equal to a plus ib. A and b are the real parts and the imaginary parts, respectively. Well, pretty clearly, if I take the magnitude of z squared, well, that's just a squared plus b squared. And that number has to be greater than, if I just drop off the a here, these are both positive terms, and so whatever z is, it's got to be greater than or equal to either one of those parts, and the b part, or the imaginary part squared. And if you look at this quantity, this is just the b, the imaginary part. The way to get the imaginary part of a complex number is to take the number minus this complex conjugate and divide it by 2i, and I think if you do that up here, you'll find that this just becomes b. And so this kind of trivial observation that the whole is greater than one of the parts when they're all positive, then you see that the absolute modulus of z squared has got to be greater than or equal to b squared, but b we write in this form here. Now we can launch into our calculation, really. The standard deviation of a squared is just this, and I can write the squared operator as just the operator times itself. And now then I can associate this one over here with this psi, and that brings it into the bra. And this one over here, I associate it with operating onto the ket. And then I just identify that this is the ket, really just call this, whatever this operator is on psi, call that, I know it's going to be another vector, state vector. And so I get a ket of f, and I just call this thing ket f. And this one over here is, of course, the bra of the same vector. To simplify notation a little bit, I guess, is if I define f to be this, then the standard deviation of a is squared is just f inner product with itself. You can do exactly the same thing for b. Standard deviation of b squared is just by definition this. Again, I can write it as the product of two, bring one of the operators operating on the bra side, the other one operating on the ket side, and then g and g. And then finally, with that definition, the standard deviation of b squared I could write as the inner product of this vector, state vector g, defined in this way with itself. With that, I can look at the product of f and g. So the inner product of f and g, just to write out what that means. Well, f was this, f ket, and g, this is bra, and this is the ket of g. And it's Hermitian operator, so I can bring this one over side here. Now, ordinarily you would do this and you'd pick up the Hermitian conjugate, but the Hermitian conjugate for these Hermitian matrices is just the matrix or the operator back on itself. And so I get this product in between, which is the same as this up here. Yeah. And then I just expand out the operator. I have to keep the order straight, so this will be A, B. I have expectation value of A, expectation value B, minus, with a minus sign. And then I'll have minus the expectation value of A times the expectation, or the times, times B. I get that one, and then finally I get minus as a plus, so I get expectation A, expectation B, and psi, just expanding this out. Okay. Now, this expectation values are all real numbers. Those are just average values. And so really what side I put them on doesn't really matter. Put this one on this side or the other. I know that the bracket of a sum of operators is just the bracket of each individual component of the sum, and then summed up. So this will be the psi bracketing AB. This quantity, a average value bracket, and this quantity here, average value, just have these in between. And then finally the last one is these two. The expectation value of this bracket is a linear operator, so when you expand out it looks like that. And then just really fess up to the fact that, well, this is just a number, so I can pull these two out. So pull them outside, and I'm left with the psi inner product with itself. I can do a similar thing up here. Leave this one the same. It's just this term. But this one I can recognize that this is just a number, so I can pull it outside here. And then I've got just the bracket of A. And likewise here, this is just the expectation value, so it's a number. Pull it out, and I've just got the bracket of B, so I get down to this form. And now that I recognize what these are, this is just the expectation value of A. This is just the expectation value of B. And since psi is normalized, this product is just 1. So I can write the first term I leave as is. This second term simply becomes expectation value of B times the expectation value of A. This one becomes expectation value of A times the expectation value of B. And this one, expectation value of A times the expectation value of B times 1. And you'll notice the order in these is not important because these are numbers here. The order is important here because these are operators. But these last three terms, the order is not important, and so I get some cancellation and ultimately come down to this expression here. That inner product of F and G is just this. And I'll just say similarly, one can take the inner product of G and F. Now I'm not going to do that here, but I would encourage you to put in a blank page in your notes and do that calculation exactly like I did above for F inner producted with G, but do G inner producted with F. And when you work through it, you'll find, or should find, this, but it would be a good exercise with the bracket notation. Now then, what I want to do is use some properties that we know about. Namely, I know this is just a complex number, right? and this is just a complex number. And what I'll do is I'll take the bracket of F and G, and I'll subtract from it its complex conjugate. But remember, the complex conjugate of a bracket is just these two switched. The order switched is just the complex conjugate of FG is just the bracket of G and F. That was one of the properties that we had earlier for these bracket symbols. And now then I just substitute these two quantities here in for these two. The first one just is this piece here. The second one is minus this one up here. And when I subtract this one, I get negative. But I subtract this, I'll get minus a minus, so this becomes positive. These two are just numbers, and they're equal and opposite, so they cancel away. And then I can recombine these back again, just pull the brackets all the way to the right and to the left. And I find that this bracket, these two, is just the bracket of AB minus BA, which is the commutator. So what we've shown at this point is this number here is equal to the bracket expectation value of the commutator, bracket of the commutator of the operators A and B. Now then, we come back to remember, I come back up here someplace. See if I can find it. Sigma A is just F bracketed with F here. And sigma B squared is just this one. And so I use those here to multiply those together. Sigma A squared is this, sigma B squared is this, and so I know that their product is the product of these two numbers. But you have to also remember, for any vectors, the Schwartz inequality, the bracket of U times the bracket of V is greater than or equal to the square of the UV bracket. And so this bracket here is the two vectors, U is F and V is G. And so this has to be greater than or equal to the bracket FG using the Schwartz inequality, and so that means that this product of the standard deviations has to be greater than that. And now then we use that other term. This is just a complex number, absolute modulus squared, and I know that that's equal to, or really a complex number modulus squared is greater than or equal to the imaginary part of that number squared. And the imaginary part of this is the number minus its complex conjugate over 2i, so the 2i is here. So I've used that property that this thing squared is 1 over 2i times the complex number minus its complex conjugate. However, we just got through calculating this. F bracket G minus F bracket G star, well, that was equal to this. That was what we just calculated. So I can substitute for what's inside there the expectation value of the commutator. So plug in the expectation value of the commutator, 1 over 2i, this thing in brackets here is just the expectation value of the commutator. Or if you like, this is really just the expectation value of this commutator, all quantity squared. So there's where the absolute square comes from. And now then, as I've said, the expectation value is this quantity, but this bracket term the commutator is inside here, and so we were back to this original statement, AB, which is what was inside. We have this, and they commute. Now, I notice there's a typo here, so make that a square bracket. So this is a commutator inside of A and B. Notice that if A and B commute, in other words, this commutator is 0, then I get that the standard deviation of A times the standard deviation of B is greater than or equal to 0. And since these are both positive, then you can make either one of them as small as you would like and still satisfy this inequality. So if the operators commute, then you can simultaneously measure both of them to arbitrary precision. On the other hand, I find the form a little bit difficult to remember the way Griffiths has it in his book, and the way I find this really just it says the same thing. It's just to me is a little bit easier to remember in this form, and in this form for this generalized uncertainty principle, if the commutator of A and B is equal to I times a Hermitian operator C, and if these two are Hermitian, this will all be Hermitian. So I times this C. Then one can re-express Griffiths' form in this form that sigma A times sigma B is greater than or equal to 1/2 the absolute value of the expectation value of this operator C that is just I factored out of it. And to me, this form has always just been a little easier to remember when I needed to apply these things. But most people they have to use a generalized uncertainty principle. The first thing they do is go look it up and make sure they understand the notation. So you could certainly pull out your copy of Griffiths and use his form, and then go through and do a calculation, which will be really using it will be the next topic.